Okay, this is the next lecture to cover my lectures for the week of September 11th, where I'm not going to be in class either Monday, September 11th or Wednesday, September 13th. I'm trying to do this from Zoom this time because I want to be able to do something in both R and on just from the looking at the PDF of the notes. So let me jump here to the notes and we'll get rolling. So where we are at is we are trying to understand the spectral representation of a random process, a spatial process. And big picture, we're looking at various ways of thinking about these random things that exist in, usually for our purposes, 2 dimensions. We have spent some time talking about Fourier things, but so far we've looked at Fourier transforms of deterministic functions. We started off with periodic functions, which led to a Fourier series. So the transform is represented through coefficients of sine and cosine waves. We then did a Fourier transform of a non-periodic function, and that felt a little bit more transform-like because we ended up with a new function. It was a function whose argument was frequency, and there still is this frequency interpretation, but it's a little bit harder to see. Where we're headed now is we want to do the spectral representation of random processes. So as the notes read here, the idea is to extend the idea of transform to random processes. And this is not entirely foreign to you because you have done transforms of random variables. And so if we think of a transformation as starting with a function and ending up with a different function which contains all of the information, if we're going to do a transform of a random variable, we need a function which describes the randomness in that random variable. And often that's the density. And so we can think of the transformation essentially in 2 equivalent ways. You can take an expectation of some function of your random variable, or this might look, of course, this is the same thing, but this might look more familiar because we're integrating out the argument of the original function and introducing this new argument t to get the transformed representation. Okay, so if the takeaway message, I'll do a spoiler alert here, the function we're gonna transform in some sense will be the covariance function, because that's the function that we've been studying and which describes randomness in this random process. But we'll see it in a slightly different way. Please do read this section in Schabenberger and Gotway. Okay, now I'm going to not follow the Schabenberger and Gotway presentation. Instead, I'm going to pull from chapter 5 of this book that came out a decade or so ago, decade plus ago, Handbook of Spatial Statistics. And this is supposed to be a chapter which introduces the spectral domain. It's written by Monsi Fuentes and Brian Rich. Brian is at NC State. Monsi at the time was also at NC State. She's moved on to do other things. But I'm going to use their presentation. Theirs is I don't know if it's more extensive than Schabenberger and Gotway's. I like it better, so that's where I'm pulling from. It's pretty close to Schabenberger and Gotway's. Notation, just if you're trying to translate between these notes, where I'm going to follow the notation that Monsi and Brian give, they're going to use y as the random thing that acts on frequencies. We'll call this the spectral density here soon. Schabenberger and Gotway use this lowercase s, which is nice because s is for spectral, but might be a little confusing because we've been using s as location. This is in their notation, this would be a function. All right, so The first thing we want to build toward is the spectral representation theorem. And the way that Monsi and Brian are Fuentes and Rich, so F and R is Fuentes and Rich, they start with the idea of building a process from random sinusoids. And they're going to first start with a finite number of these sinusoids. So quoting directly from this chapter, they say, suppose y1 through ym are mean zero complex random variables. So this random thing takes on a real part and an imaginary part. It has it has cross expectation of zero so long as I and j are not equal. So essentially what this is saying is y1 and y2 don't share any information. The expected value of yj squared, this is the absolute value means since y is complex, the absolute value would be y times y's complex conjugate. That gives you the magnitude of the random, that gives you the magnitude of a complex number. So we extend variance in some sense is magnitude. So this makes sense for the sense of variance in the complex setting. What we have are we have m y's, we have m frequencies, which are going to be given by omegas, and they say consider this process here. So what they're doing is they're going to take here's our, this might not, remember this is really a sinusoid because e to the I stuff is cosine I stuff plus I sine stuff. So this has a cosine piece and a sine piece in it. We're going to multiply it by some random coefficient is the way I'm going to think of this y. It's complex, but it's still just getting a magnitude in the complex sense. And we're going to sum up m of these sinusoids, which each have presumably different frequencies. Okay, so if we construct such a random process z, then Fuentes and Rich say that this random process that we've generated, z, is a weakly stationary process. They say an RD, but I'm 99% sure that's a typo, and they meant to say, no, I take that back. They do mean random process in RD. The RD is saying that the S takes on the location is in the d-dimensional reals. We usually think in two-dimensional reals, but this z is going to be complex. So RD is in fact correct. I have a typo here in the notes, which I'll correct hopefully at some point, but this z is complex valued. That's what's important here. And not only, and they say that if we construct this z, the covariance is given by this expression, where we can see that somehow those sinusoids carry over, and then we've got fj. Fj we can think of as the variance of our random yj's. Okay, so there's a lot here. We're going to spend a couple of pages talking about this and extending it, but right now we're dealing with a finite number of sinusoids. We've got m of them. We've got a countable number of frequencies. Both our frequency vector and our location in RD. This is just the dimension of our process. And of course, when I take this d-dimensional vector times this d-dimensional vector, that gives me a number. So our z is a scalar. It's a single number but in the complex number. So of course it has a real and imaginary part. I don't love the notation here. The S here is I think of it as a location in space. The S here is a lag. Our covariance function is really talking about the covariance between our process Z at two different locations it simplifies down to a single argument in the stationary case, and that argument is of lag. So you'll see that I'll introduce some H's later, but we're going to have to be careful about thinking about this vector S, whether it's a location or whether it's a lag. Okay, so let me jump to R and just illustrate this. You probably have a good idea of what this might look like, but let's do it anyway. Okay, so here is R. All right, hopefully you're seeing my R screen, and I have added it to our spatial processes.r file, so this will be posted on Canvas soon. That I don't really, I'm not sure I want to do that. Well, let's see. Okay, first thing I'm going to do is I'm going to just talk about a random sinusoid. This is the main purpose of this is if you're a little bit uncomfortable with these complex coefficients, these complex random variables, hopefully this will illustrate it for you. So I'm going to let omega take on the value of pi. So consequently, our period of our wave is going to be 2. I'm just going to plot it from 0 to 10. And then you can see what I'm doing here. That we had that e to the I omega stuff. I'm doing that here in line 145. If I expand that out in terms of cosines and sines, the cosine bit is omega times s. The imaginary bit, I should say, the real bit is cosine omega s. The imaginary bit is sine omega s. And so this is going to store this as a complex number. And if you want to see that in R, here is the values of our E piece at the first 5 locations S. When S is 0, cosine returns 1, sine returns 0. And so this first number here should make sense. I'm going to plot the real piece. Shoot. Well, one more time. No. Shoot. Okay, well, let me pause the recording at this point, and I will pick it up here in just a minute when I sort this out. Okay, we're back. Apparently, our studio wants me to install a new version of R, and I don't really want to take the time to do that. So we're going to try and do this a little bit differently. I'm going to just try and share my screen here. And so you should be seeing all of my R here. And so let me just go through this again. Where we were was we said the E piece of this is, I'm thinking of the pieces within my summand. Right now, I've only got one piece because I'm just doing a single wave. The E really has a cosine and a sine hidden in it. We ran this where we saw the value of 1 and 0 at s equals 0. And then what you're seeing over here is here is the real piece. This is the standard cosine wave with period 2. This is the standard sine wave with period 2. There's nothing random yet. So now we're going to introduce a random complex coefficient. the way I'm going to do that is I'm going to draw two random normals. So I got 0.37 and 0.12 here. I'm going to create a complex number from those two just by calling the first one the real bit and the second one the imaginary bit. Now I'm going to apply it to my wave. So I'm going to take y times the e piece. And so I create my random wave. My random wave has a real part and it has an imaginary part. So if we think of this as our location in space, we're introducing something random. It, of course, is going to have a period of 2. Both of these waves have period 2. The magnitude of the wave is random, but also the shift of the wave is random. And we'll see that if I run this random bit and apply it to our E piece each time, you can see that the magnitudes are changing. You can also clearly see that where the wave begins is changing. So in that sense, we've created a random wave. What Fuentes and Rich are saying is let's create a spatial process by summing up several of these. So I'm going to do this with 3 sinusoids. I'm going to choose 3 different frequencies, which I'm calling omega 1, 2, and 3. I have to get the corresponding waves, both real and imaginary. So that's what's being done here. You can see that the omegas are being applied. And now I need 6 random pieces. I've got 3 waves, each with real and imaginary parts. So I'm going to draw 6 normals. I'm going to create 3 complex y's from those random normals. I'm going to create 3 waves, and I'm going to create the combined wave. So now I think let me do this. And so here is my random wave, my first random wave. Right now, I'm only going to plot the real part. There is an imaginary part that comes along with this. You saw that before. But I'm not going to draw pictures of that. That is also here, however. So there's wave 1, there's wave 2, there's wave 3, which looks, oh, that's actually wave 2 because I forgot to advance my cursor. There's wave 3. If I combine them, here is that overall wave. So let me try that again. Sorry. So one more time. Okay, so here was that random wave 1, here was that random wave 2, here is random wave 3, and here is the combination of those. What we can see is that overall, we're getting this kind of long scale behavior, which is kind of hidden by the wave with higher frequencies. But we do see that overall things kind of go up and down according to this long wave. A lot of this is being driven by that smaller wave, and that's because it has the greatest magnitude in this realization. If I run this again, here is one where these 2 waves are interacting in kind of an interesting way. We do see the wave with the long wavelength, low frequency. It carries over, but it's kind of being driven largely by these, which interact in kind of a fun way there. And what we can see is if we just view that bottom graph, we get interesting random processes. So let me jump out of R now. And jump back to my notes and say, okay, so where are we? All we've done is we've illustrated this. We're going to take a finite number of sinusoids and we can create a spatial process from that. So if you look at the Fuentes and Rich book, they have this plot where they are showing two examples. They're going to do this from many more waves than 3 waves. I did it with just 3 waves so that we could see how the waves assemble into a random process. They're going to do this with 100 different waves. They're going to do this with 2 different ways of generating those random variables y. The first one has, so on the x-axis is frequency, on the y-axis is the f, that's the magnitude of the variance of this complex number. The low frequencies have high value for f, the higher frequencies have lower value for f, and so what a one single realization of this random process looks like this. If we change the value of what they're going to call the spectral density, just think of the f's, what they're doing now is they're allowing the higher frequencies, they're allowing the coefficients with the higher frequencies to have larger variance. So there's a possibility that they're going to take on a larger value. What you introduce is a different type of random process, which is more wiggly because the higher frequencies are contributing more to the overall power. That if that word doesn't mean anything to you, it will, but the higher frequencies are contributing to the overall power in a larger sense in the second example than in the first. Okay, this fj is, as they say, is called the spectral density function, and we'll understand that a bit more soon. Continuing on with this finite number of waves example, they give this expression for the covariance, but they don't develop it. And so let me just take a minute to develop it. So we start off with this expression z. This is our recipe for generating this random process z. It arises from summing up these sinusoids. We can easily see that the expected value of z is 0 because the expected values of the y's are 0. And so we want to talk about the covariance of z at location S and at location S plus H. So this should look familiar to you. This is getting to the covariance at lag H. These z's are complex, and we need to understand what this means. The covariance of two complex random variables is defined this way, where it's the expected value of x1 times x2's complex conjugate minus the expected value of x1, expected value of x2 complex conjugate. So it's the usual definition of covariance, except we take the complex conjugate of the second random variable, which of course is complex. So that's how I get from here to here. We can see that I have expected value of z times z star, which is the complex conjugate. And then because it's mean 0, I've just got a 0 here on the end. All we've got to do is focus on this bit. I can write down the expression for zs. I can write down the expression for zs plus h. For zs, I'm going to use j as my index. For zs plus h, I'm going to use k as my index, just so that I can keep them distinct. But you can see that basically the only difference other than that change of index is I've got an s plus h here. And I guess importantly, I introduced this negative sign because this is complex conjugate. So this would be cosine of stuff minus I sine of stuff. Okay, so I can switch the order of my sums and expectations. So I've got my double sum out here. I've got the e to the I omega j part. I've got the e to the negative I omega k part that comes from here. I'm going to write this expected value of sums as a product of expectations. So I have my h piece here, and I've got the expected value of yj and yk. So what I'm going to do then is I'm going to look at this part. I'm going to write it down in terms of its cosines and sines. So I have cosine stuff plus I sine stuff. and I've got cosine stuff minus I sine stuff. I expand that out, just doing my usual foiling. I've got cosine, cosine. I've got a plus I sine cosine. I've got a minus I cosine sine, and I've got a sine times sine here. We said that these functions are orthogonal. We saw it in the finite dimensional case, but it does carry over into this, or I should say that not finite dimensional, I should say in the discrete case, we saw that these cosine and sine basis functions were orthogonal. That continues to be true. And so all of these pieces are going to be 0 unless omega k equals omega j. If that's true, then this becomes cosine of omega j squared. This is sine omega j, cosine omega j, and then we've got cosine omega j, sine omega j, and I've got plus and minus. So of course the I pieces, the middle pieces drop out. And then I've got sine of omega j. And this is just a cosine squared term. This is a sine squared term. And so this equals 1. So what this says is this is a big fat 1 if k equals j, and it's a big fat 0 if k does not equal j. So we're just left with this expression here. Here is our, I probably should have a y star here, but this is our variance of our y bit. And so that's where the fj comes from. And we have our exact expression back here that Quintus and Rich just handed to us without explanation. Mine would be, of course, in terms of h's rather than s's for the notation bit that I talked about before. All right, I'm going to pause. I'm going to stop this recording, and I'm going to do another recording for the remaining notes.